Hello dear students. So in the B2A series, today we are going to start with modern physics. Now in modern physics, the topics that we cover are nuclear physics and radioactivity. We will try to cover them both today. So let me start with nuclear physics. So, so in nuclear physics, we talk about the nucleus of atoms. Okay, we talk about nucleus of atoms, and as you would be knowing by now that nucleus is a very small part of the entire atom. Okay, uh, very small as compared to the entire size of the atom. Okay, and we are going to deal with it, and therefore whatever particles are present inside the nucleus, as of now we know that protons and neutrons are part of nucleus. They are present inside the nucleus, and when we start dealing with their masses, okay, their masses are so tiny that kg becomes a very inconvenient unit to talk in terms of kg, if we want to discuss masses. So therefore we take care of, we use another unit which we call as AMU. Okay, so let me first talk about the unit of mass that we would be using. So we would be using AMU. AMU is atomic mass unit as the unit of mass, where we are dealing with subatomic particles. Okay, so one atomic mass unit is what? Okay, let me write the full form also. It is atomic mass unit. By definition, this is 1/12 of mass, 1/12 of mass of a neutral C12 atom. Okay, now C12 atom is carbon, the isotope of carbon, the mass number of which is 12. Okay, so it is 1/12 of the mass of a neutral C12 atom, that is 1 AMU. Its value is somewhere close to 1.67 into 10 raised to power minus 28 kg. All right, so that is the weight, that is the mass, that is the value of 1 AMU. That is 127 actually. I wrote it incorrectly. Okay, so 1.67 into 10 raised to minus 27 kg, that is 1 AMU. Okay, now apart from this, what we would be needing is mass of a proton. Okay, so mass of a proton is slightly more than 1 AMU. This is what you have to remember. 1 AMU is also represented as mu. Okay, mass of neutron, okay, is also slightly more than 1 AMU. Okay, slightly more. Okay, the difference is not too much, and mass of a neutron is greater than mass of proton. Okay, so I want you to remember this, that mass of proton and mass of neutron, it is more than 1 AMU, but the difference is not too much. Like mass of proton is somewhere around 1.00 and some numbers AMU. So the point to remember is that it is strictly not 1 AMU, it is more than 1 AMU. Same goes with the mass of neutron. Okay, mass of electron is very small as compared to the mass of these two entities. Okay, it is mass of electron is around 1 by 1840 times the mass of proton. Okay, so these are the things that you need to remember regarding the mass of neutron, proton and electron. Okay, next thing, if we want to talk about composition of a nucleus. Okay, composition of nucleus. So okay, suppose I'm talking about a nucleus in which Z is the atomic number. Okay, now atomic number would be the number of protons present in the nucleus, and A would be the mass number. Mass number indicates the total number of protons plus neutrons. Okay, so this is number of protons and this is number of neutrons plus number of protons. Okay, so this is a nucleus. If I represent it, I will say that it contains Z protons, okay, and it contains A minus Z neutrons. Okay, now there is something to understand here which we call as mass defect. Now what exactly is mass defect? Let me highlight that to you. So consider a C12 nucleus. Consider a C12 nucleus. If I talk about what is the expected mass of this nucleus, okay, so what is the expected mass? Are we going to say that it would contain 6 protons and 6 neutrons? So 6 times the mass of proton plus 6 times the mass of neutron. That is the expected mass of the nucleus. Can we say this? Okay, and if you are agreeing to this, that it is 6 times the mass of proton and 6 times the mass of neutron, and we also know that mass of a proton and a mass of a neutron, they are both more than 1 AMU, then this number is certainly more than 12 AMU. Do you agree with this or not? Okay, it needs to be more than 12 AMU. Now this is the mass of nucleus. Okay, now what is the actual mass of a C12 nucleus? Let's pay attention to that also. If we are defining AMU as 1/12th of the mass of C12 atom, then obviously the mass of a C12 atom would be 12 AMU. But here we are not writing the mass of atom, we are writing the mass of nucleus. So I must subtract the mass of electrons. I must subtract the mass of electrons from the mass of atom to get the mass of nucleus, and this is what we are getting, which is certainly less than 12 AMU, because this is 12 AMU minus something. Okay, so the expected mass is more, the actual mass is less. Where did the mass go? Okay, like how is it happening? Okay, if we are expecting this to be the mass, then why is the difference? So let's try to understand this. So let's talk about the day this atom would have been formed. Okay, it might have been the origin of universe. Okay, or whichever day when this atom was born or it was created. The protons and the neutrons, they were far apart from each other. Okay, initially, like they got very close to each other to constitute the nucleus, but before they did that, they were far apart from each other. So then what happened, that they congregated. Okay, they came together, they started influencing each other, they came together and they formed a very dense structure called the nucleus. They all got packed into this dense structure. Okay, now I'm just counting how many neutrons, and so 4, 5 and 6. Okay, so they got packed in a very, very dense structure. Now, just in case if you are wondering that we pushed them together and then we packed them in something, then understand this, guys. If you are, that is how we picture a nucleus, that is how we draw a nucleus. We draw a boundary and then we draw protons and neutrons in it, which makes us believe as if the nucleus is a sack in which the particles have been thrown and they have been pushed together. If that is the case, then the question would obviously be that what is this sack made up of? Okay, remember, it can't be made up of atoms and molecules, because we are within an atom now. Okay, we are within an atom, and nucleus is a subatomic particle. So this sack what is this made up of? If it exists, the right thing is that there is no sack. Okay, there is no sack. So when we think of a nucleus, it's just a volume where the particles have came together and they are somehow sticking together. When I say somehow, there are reasons for these particles to stick together. We call these forces as the nuclear forces. So the nuclear forces make these particles stick together, and these are short range forces which are not operational when the distance becomes too large. Here, too large means anything more than 10 raised to power minus 15 meter. Okay, so when the distances go out of this range, that means even within an atom, even within the atom, remember the radius of orbit in a hydrogen atom, the radius of the first orbit, that is in angstroms, 10 raised to power minus 10 meter. So even that distance is an infinite distance for this force. So the force that I'm talking about, nuclear force, it is operational at very small ranges, and these ranges are smaller than the size of an atom, and therefore they will only be seen inside the nucleus, and therefore we call these forces as nuclear forces. So the nuclear forces bind these particles together. Okay, and that's how a nucleus is constructed. But when this process of getting together happened, okay, during this process, each particle here donated a fraction of its mass. Okay, each particle here donated a fraction of its mass, and this mass is called as mass defect. This mass was lost. It was converted into energy. The Einstein equation, E equal to mc square, the very famous equation, we'll talk about that in a short while. But Einstein equation tells us that energy can be converted into mass. Yes, guys. What are the implications of this statement? Or let's first talk about this. We'll come back to this. We'll come back to this. But first, let's talk about the energy and mass equivalence. Then we'll continue our discussion of mass defect. So, energy mass equivalence. What does this say? Okay, this say that mass and energy are interconvertible. So yes, you can take a lump of mass and you can convert it into radiations. So the entire mass can be converted into energy. It can be converted into radiation, and the reverse is also true. Theoretically, it is possible to convert radiations into mass. And what is the conversion equation? That is the famous equation from Einstein, E equal to mc square. So that is the equation. Okay, E equal to mc square. Okay, now what does this equation tell us? That if 1 kg mass, if it is completely destroyed and converted into energy, then it would give us about this much amount of energy, which is around 9 into 10 raised to power 60 joules. So massive amount of energy. Similarly, we can say that 1 AMU, we can calculate it. 1 AMU would be equivalent to 931 MeV of energy. Remember this. People generally use 931.5 also. Okay, but because that's the fourth significant digit, that will not make too much of a difference in the calculation. That is the fourth digit. Okay, so 1 AMU is equal to 931.5 MeV. That means when 1 AMU gets completely destroyed, the amount of energy that is produced is 931.5 MeV. Now, going back here, this is what happened. All these particles, they donated a fraction of their mass. Okay, and that mass is called mass defect, and that got converted into energy. So when this nucleus was formed, the constituent particles, they came together and they gave a portion of their mass into the form of energy, which flew away, which has gone. Okay, if you give this energy back to this nucleus, then the nucleus will again split into the constituent particles. So if we have to break the nucleus, then we have to supply the energy that was released at the time of formation of the nucleus. Okay, so this energy is called the binding energy. Delta M is called the mass defect. So here, the difference of this mass and this mass would be called the mass defect. Okay, and mass defect multiplied by c square is called the binding energy. Binding energy is the amount of energy released in the formation process of the nucleus, or you can also say that it is the minimum amount of energy that we need to give to the nucleus to break it into the constituent particle. When this nucleus breaks into constituent particle, the energy that you have supplied, it gets converted into mass again, and that mass appears as as the complete proton. This proton gave a fraction of its mass to convert into nucleus, but when it comes back in the form of a full proton, when the particles again come in their raw form, like how they were before the formation of the nucleus, then we see the complete proton and the complete neutron. Okay, so I hope we are clear with what binding energy is. Okay, so binding energy is a term that you need to remember. It is the amount of energy released in the formation process of a nucleus, or you can also say that it is the amount of energy that we have to provide to a nucleus so that it breaks into constituent particles. Okay, now there is something called as binding energy per nucleon. Okay, binding energy per nucleon. What is nucleon? Protons and neutrons, they are collectively called as nucleons. Okay, so binding energy per nucleon. Okay, so what it would indicate, if I go back here, okay, binding energy per nucleon. Here the nucleon count was 12. So can I say that binding energy per nucleon will indicate that time at 12, the contribution of mass, the contribution of mass coming from each particle in the process of creating the nucleus. So binding energy per nucleon is a measure of how much every individual particle contributed in the formation process of the nucleus. It's something like this, that let's say 100 men decided to form a city, and to do that they all donated an amount. Okay, so the total amount that they donated for the city to form is the binding energy, and whatever was the total amount, that divided by 100 is the average amount donated by one person. So that is the binding energy per nucleon. So when nucleons, the nuclei with higher binding energy per nucleon, they are the more stable ones. You can say that. So it's a, if you just take an analogy from a real life, there are 100 men who decided to create a city and they donated some amount. Then there were, let's say, 50 men who decided to create a city and they gave more amount. So can we expect those 50 men to be creating a better city because individually they are contributing more? So if that is the case, then you can say that yes, the binding energy per nucleon is higher for the case when the 50 men came together to create a city, and because they individually contributed more, we can say that their city would probably be a better one, a more stable one as compared to the city created by 100 people. So binding energy per nucleon is the measure, is the measure of stability criteria. Is the measure of stability criteria. Higher the value of binding energy per nucleon, more stable the particle is. Now we know many elements. Like in periodic table there are more than 100 elements, and many elements have got isotopes also. It is important to understand here that while the chemical properties of isotopes are almost identical, their nuclear properties may vary significantly. And why is that? Let's try to understand that. The chemical property of any element, it depends on the electron configuration, how electrons are distributed in the orbits. That is the governing factor for chemical properties. And even in isotopes, the same number of electrons are there, the same configuration is there, so their chemical properties remain same. But nuclear properties are a matter of nucleus. So in isotope, you have different count of neutron within the nucleus. So the nuclear property of isotope can be significantly different while their chemical property remains same. So coming back to the idea, I was saying that there are more than 100 elements in periodic table, and on an average we can say that every element has, on an average has 2 or 3 isotopes. So there are about more than 300 nuclei to be discussed. 300 type of nuclei, maybe 250, maybe 200. Let's take the number is not a concern. The point is that we have many different kind of nuclei, and as of today we know the binding energy of almost all the nuclei. Through experiments we have discovered that. So we know the binding energy, therefore we can also talk about the binding energy per nucleon. So I have many nuclei, many different nuclei. I have binding energy per nuclei for all those nuclei. So what I'm suggesting is that we can create a graph. We can, like, if the mass number is 1, for example, if we are talking about hydrogen, there would be a certain value of binding energy per nucleon. If the mass number is 2, certain value. If the mass number is 3, certain value. So we have this data for various values of mass number. We have various values of binding energy per nucleon, and if we make a graph of binding energy per nucleon versus the mass number, what we get is a graph like this. So first of all, I am not drawing a continuous graph, and in this graph also there are local variation. One x will be higher than the lower, then again higher than, but overall shape is this. Now first question, why I did not draw a continuous graph? Because it's not that I can get any value of mass number that I want, like 1, 2, 3, 4. These are the values of mass number that I will be getting. I won't be getting 1.1, 1.2, 1.3. So the graph cannot be continuous. Although I can connect these lines, that's a different issue. But ideally, when you are making this graph, you will be having specific points. Now if you want to connect them, you can connect them. What you will discover is that this graph has a maxima, and this maxima happens at iron 56. So iron 56 has the highest value. It has the highest value of binding energy per nucleon, and that is around 8.8 MeV. That is around 8.8 MeV. So remember this, and the fact that this graph possesses a maxima is a very significant fact. It plays a very important role in understanding and in discovering one thing. I'll talk about it in a short amount of time. So this is binding energy per nucleon. Now let's talk about the Q value of a reaction. What exactly is Q value of a reaction? Let me talk about that. So suppose a reaction took place something like this. There was a nuclei A with a mass number of, let's say, 20. There was a nuclei B with a mass number of, let's say, 26. And then these two nuclei, they got together and they separated to form two nuclei. let's say, which was 22 and 24 in number, something like this. So A and B got together and they then created two new nuclei, C and D. Okay. Now, if we want to execute this reaction, what we need to do? We first need to break A. Okay, we need to break A into constituent particles. So that I get 20 nucleons. You know, we need to split A. Okay, we need to split B. Okay, so now we will have the constituent particle. So I took A. Remember, A is a ball containing many particles. Okay, I broke A. Now I have a lot of particles with me, protons and neutrons. I took B, I broke B, and now I have a lot of particles, protons and neutrons. I have a collection of a lot of protons and neutrons coming from A and B. Now I am regrouping them to form C and D. You know, I'm collecting some protons and neutrons together so that C is formed. I'm collecting some B and C and D together to, okay. So you have a collection of particles, then you create C and D. Okay, now in this process, what did we do? We broke A, we broke B, and then we created C, we created D. So in each of these steps, some energy transaction has happened. For example, if I'm trying to break A into constituent particle, I had the nucleus of A and I'm breaking it into constituent particles, I would be required to supply energy. I need to give energy to A, and how much energy do I need to give? I need to give it its binding energy. Okay, so the energy supplied, okay, the energy supplied would be written as the energy that I'm supplying in this process. Okay, energy supplied would be binding energy of A, and similarly to break B into the constituent particles, I would be supplying binding energy of B. Okay, now what is the energy that I received? Okay, energy received. So when I put these particles together, they congregated to form C. So the binding energy of C got released, and similarly the binding energy of D got released. So what is the net energy that I got from this reaction? So this is the total energy that I'm getting. This is the total energy that I supplied. So what is the net energy gain for me? What is the net energy gain for me? That is called the Q value. So Q value means the energy released in a reaction. And in the previous reaction, it would be BEC plus BED minus BEA plus BEB. Okay, so it would be, we can say for a general reaction, we can say it is the sum of binding energy of product, okay, minus sum of binding energy of reactants. Okay, we can also write Q value in terms of mass. You think about this and tell me, suppose if the Q value of this reaction is positive, which means that this reaction is releasing energy. Okay, so this reaction is releasing energy. So that would mean that we write a plus Q here. Like A and B, they are breaking into C and D, and then they are releasing some amount of energy. If I ask you that on which side should we expect more mass, like before the reaction happened, the total mass was something. After the reaction happened, the total mass was something. Where do you think the mass is more? On the side of reactants or on the side of products? Because if I'm saying that there has been a net release in energy, then obviously this energy would be coming from the destruction of some mass. So we can expect the mass of reactant to be more than the mass of product. So the another way to write Q value is mass of reactants. Notice that when you are dealing in terms of binding energy, you are doing product minus reactant. But when you are dealing in terms of mass, you are doing mass of reactant minus mass of product into C square. Even this is equal to the Q value of the reaction. Okay, even this is equal to Q value of a reaction. All right. So if we are good with this, okay, which we should be. Next, we can actually talk about a question. Okay, let me give you a question. Okay, so the question is somewhat this. Okay, suppose I give you a hypothetical graph. I told you that the significance of having a maxima in between, I will explain that. So suppose we are talking about a hypothetical graph like this. Okay, so this is binding energy per nucleon and this is the mass number. This is a fictitious graph. It's not a real graph. Okay, but it conveys the point. So let's talk about this. And also this is a question that came in JEE Advanced. Okay, it's a question that has come in JEE Advanced. So let's say this is 50 and okay, this is 100. Okay, and let me assign some values here also. So let's say this is 5 MeV. Okay, let's say this is 6 MeV. Okay, let's say this is 8 MeV. Okay, so hypothetical graph it is. Okay, now I'm giving you two reaction. One reaction is this: A30 meets B40 and it gives us C70. One is this reaction, and the other reaction is that D140 changes to 2 times of C70. Okay, so these are two reactions, and we want to calculate the Q value of both the reaction. Okay, so the question is find Q value of both reactions. So how do we do it? How do we find the Q value? So first of all, from this graph, do we know the binding energy of A? Okay, we will have to read the information from the graph. The graph conveys us a lot of information. We have to read it and we have to use it. So for any nuclei with a mass number up to 50, the binding energy per nucleon is 5 MeV. So even for A has a mass number of 30. Okay, so for A, binding energy per nucleon is 5, and therefore binding energy would be 5 into 30. Okay, so if I want to write Q value of the first reaction, okay, I will write binding energy of C, binding energy of product minus binding energy of A plus binding energy of B, and we will read the value of binding energy of C in a same manner. So binding energy of C would be how much? C has a mass number of 70. At the value of 70, the binding energy per nucleon is 8. Okay, so 8 multiplied by 70, how much is it? 8 into 70. Okay, 8 into 70, that is 560, minus binding energy of A and B. A and B both have mass number less than 50, so we are operating in this zone. So 5 is the binding energy per nucleon. So we will write 5 into 30 minus 5 into 40. So in other words, this is 8 minus 5 into 70. Okay, so this is 210 MeV. Okay, so that's the Q value of the first reaction. So because Q value is coming out to be positive, it means that the energy is being released. Okay, it would mean that the energy is being released. Similarly, if we calculate the binding energy of the second reaction, okay, in a similar manner, the Q value of the second reaction. So the product is C70. So C has a binding energy per nucleon of 8, and we have two nuclei of C. So 2 times of 8 into 70 minus the binding energy of D. Okay, so the mass number is 140, so we are in this zone somewhere here. So the mass, the binding energy per nucleon is 6. So 6 into 140 would be the binding energy of D. So 6 into 140. Okay, yeah. Okay, so how much it is? So 140 can be taken out as the common quantity, and this will become 8 minus 6. So this is 2 into 140. So this is 280 MeV. Okay, this is 280 MeV. So even this is positive. So both the reactions are releasing energy, which is quite surprising. You know, in one reaction there are two nuclei which are combining, and we are getting a larger nuclei. And here a larger nuclei is breaking, and yet we are. So what exactly is happening? Like when two nuclei combine, then also we get energy. When a larger nuclei break, then also we get energy. How is it? The reason is that, or the right way to think is that, whenever the product that we get, if it is higher on this graph, then it leads to more stability. Okay, it leads to more stability, and therefore we are getting energy released in both the cases. Now this reaction, this kind of reaction is called fusion reaction. Okay, in fusion reaction, two or more nuclei merge to create a larger nuclei, and this one is called a fission reaction, in which one nucleus breaks into the smaller nucleus. Okay, so the fact that there is a maxima in this graph allows us to generate energy via fusion as well as via fission. Okay, we take nuclei from this region, and if we break them into smaller one which belong to this region, then energy is released. Or if we take nuclei from this region, the lighter ones, and we merge them to form nuclei of a slightly higher mass number, such that the product belongs to this region, then again the energy is released. So we are able to generate energy from fusion as well as fission because of the fact that the graph is higher in the middle. Alright guys, so that's about okay, we can talk about some common. So guys, there are some common Okay, we can also talk about radioactivity now. So what exactly is radioactivity? Okay, so there are nuclei which are unstable. Okay, like they decompose, they disintegrate by themselves, especially the larger one, especially the ones which have large mass number, so which lie on the downward slope of that binding energy per nucleon graph. Okay, so there are nuclei which are unstable and they disintegrate. So this process is called radioactivity. So if I have to define this, radioactivity is the spontaneous disintegration of unstable nuclei into daughter fragments. So okay, so this is what is radioactivity. It is the spontaneous disintegration of unstable nuclei into daughter fragments. What does the word spontaneous means? It means that it happens by itself. We don't have to induce it. We don't have to do any kind of changes. It just happens by itself. Okay, so that is what the radioactivity is. We measure radioactivity in what we call as disintegrations per second, like DPS is the unit. Okay, so or we define activity. Okay, so what is activity of a radio sample? But before I talk about activity, let me talk about the common modes of decay. Okay, the most common modes of decay. So what are they? Okay, like the most common reactions that we see. So the first one is alpha decay. Okay, it's called alpha decay. So what is an alpha particle? Okay, an alpha particle is basically a doubly ionized helium atom, or very simple, it's a helium nucleus, or you can simply say that it is helium nucleus. That's it. That's alpha particle. Okay, it's a helium nucleus, which means it is basically a collection of 2 proton and 2 neutron. Okay, so how does, like, what happens when alpha decay happens? So suppose there is a nucleus with mass number A, atomic number Z, and then it breaks into another nucleus. Okay, let me depict it here also. So we had a nucleus X in which there was Z protons and A minus Z neutrons. Okay, so it converted into Y by throwing out an alpha particle. And when I say that it threw out an alpha particle, it means that it threw out 2 protons and 2 neutrons. So we would have Z minus 2 protons here, and we would have A minus Z minus 2 neutrons here, and the alpha particle, that is 2 protons and 2 neutrons, would be emitted. So this breaks into a new nucleus because the atomic number is different. Therefore, I have changed the symbol also. Okay, because now it's a new element. Okay, and the mass number decreases by 4. Okay, and we get what we call as alpha particle. So this entity is called alpha particle. So when this reaction happens, okay, like if we have a container containing only X, so from the container some of the X will change into Y and some alpha particles will be thrown out. So if I have to depict it in a picture, okay, so let's say this was a container and it was containing only X. Okay, and let's say I'm denoting X with dots. Okay, so these are X nuclei. Okay, so initially we only had X nuclei. Okay, after some time what we would witness, is that in the container, apart from X, okay, there are X nuclei, but apart from X there are some other nuclei as well. Okay, and these are Y nuclei because X has been getting converted into Y. And not only that, we would see some particles flying. Okay, these particles would be flying. Okay, they would be flying here and there. So these are alpha particles which are getting ejected. So okay, so this is what we mean. So this was only X, now this is X, with a collection of Y, because some of the X got converted into Y and they threw out alpha particle. So the energy released in the reaction, the Q value of the reaction, is released as the kinetic energy of the daughter particles. In this case, in alpha decay, most of the kinetic energy is taken up by alpha particle itself. Okay, so that's about alpha decay. The most important fact for you to remember is that in an alpha decay, 2 protons and 2 neutrons are lost, and therefore mass number decreases by 4 and atomic number decreases by 2. This is the most important fact that you need to remember. This will be used in framing questions at your level. Okay, now what are the other kind of decay that we can talk about? So the second type of decay is called a beta decay. Okay, second type of decay is called a beta decay, and actually there are two kinds of beta decay. One is beta negative and the other is beta positive. Okay, so we have beta negative decay and we have beta positive decay. Now, what's a beta negative decay? So before that, we need to talk about what is a beta particle or beta negative particle. What exactly is this? Okay, a beta negative particle is nothing but an electron. It is simply an electron. Okay, it is simply an electron, but this electron is formed within the nucleus, but sir, there is no electron in the nucleus. Yes, it is not. It is created in the nucleus and then it is thrown out of the nucleus. It is ejected out of the nucleus. Okay, now how does this happen? So what happens is that a neutron which have atomic number of 0 because it doesn't have any charge and a mass number of 1, it converts into a proton, okay, which has the atomic number 1, a mass number 1, and it converts into an electron. And there is another particle into which it converts, which is called an antineutrino. Okay, you can forget about antineutrino right now. Antineutrino is a chargeless and a massless particle. Okay, you haven't come across antineutrino yet, so you can just forget it. The point is that one of the neutrons within the nucleus gets converted into a proton, producing an electron with it. And why the electron produced? To keep track of charge conservation. Okay, initial charge was 0, final charge needs to be 0. Okay, now this is chargeless as well as massless, so on both occasions I'm writing 0. Okay, so this electron is thrown out and it is this electron which becomes the beta particle. It is this electron, okay, which we call as the beta negative particle. So if this reaction is taking place in a nucleus, then what can we expect? Like, suppose X, A, Z. Now, if one of the neutron is converting into a proton, Z will increase by 1 and therefore we should change the symbol. But the mass number still remains same. What do you think? The mass number still remains the same. Okay, because a neutron is lost, a proton is born. Okay, so mass number is, and we get an electron. Okay, we get an electron and we get an antineutrino. So this is what we call as beta particle. Okay, this is what we call as beta particle. Okay, and similar to the case of alpha, okay, this beta particle will be thrown out of the nucleus. So again, in this reaction, what happens? You have to keep that in mind. In a beta negative decay, mass number remains the same, but the atomic number increases by 1. Okay, now we can talk about a beta positive decay also. Okay, now what is a beta positive particle? Okay, what is a beta positive particle? So a beta positive particle is a positron. Okay, now you may have heard this word, you may not have heard this word before. What is a positron? We have heard about proton, we have heard about electron. What exactly is a positron? So a positron is a particle, the mass of which is same as the electron, but its charge is plus E. Like, the charge is equal to the charge of proton, but the mass is equal to the mass of electron. So you can either look at it as a positively charged electron, okay, that's a positron, or you can look at it as a very light proton, a proton whose mass is actually equal to the mass of electron. So whatever way you want to consider it, the point is that its mass is same as mass of electron and its charge is plus E. So it's a positively charged electron. So what happens like in the nucleus? So in nucleus, sometimes a proton decides to get converted into a neutron, and then to keep track of charge conservation, a positron is given along with a neutrino. So neutrino is again a chargeless and a massless particle, but it is capable of carrying energy and momentum. And if this reaction we have to depict, okay, then how will we depict it? So one proton is lost. Okay, so the Z will decrease by 1, but the mass number will remain the same. And then we'll have a positron, which is actually the beta particle, and the neutrino. Okay, so this is our beta particle. Okay, so Remember this. Okay, guys. All right. So we have talked about finally the third most common decay, which is called as gamma decay. Okay. So what exactly are gamma rays? Okay. So unlike the case of beta particle and gamma alpha particle, so alpha particle and beta particle, they are particles, and a stream of alpha particle, like many alpha particle coming together, would be called as an alpha ray. Alpha ray. Similarly, a stream of many beta particles, either beta negative or beta positive, coming together, they would be called as a beta ray. Okay. Similarly, we have a gamma ray. But unlike alpha and beta particle, gamma ray, they are not a collection of particles, but they are a collection of electromagnetic waves. Like these are waves only. These are rays. Okay. These are electromagnetic rays. Okay. Okay. So these are actual electromagnetic waves. The other two were particles, a stream of particles. Okay. So when does gamma rays are produced? So generally what happens when alpha and beta decay happen, or when any kind of decay happen, then after the decay, what happens is that the product that we get, many times that product is in a very excited state. Okay, like it has more energy as compared to what it should have in its ground state. So it gives out that energy in the form of radiation, and that radiation is called gamma rays. These are highly energetic value, like their energy is more than X-rays also. Okay, so their energy ranges from MeV to keV, like kilo electron volt and mega electron volt. In that range, the energy of one photon lies. So highly energetic rays, harmful for human body. Okay, so generally after alpha and beta decay, gamma decay also happens, because the product that we get, okay, the Y nuclei that I've been drawing in all the equations, that product is often in its excited state, and when it jumps down to the ground state, it emits radiation, and those radiations are called gamma rays. So from the point of view of framing question, you just need to know that gamma rays are actually radiations. They are electromagnetic waves only. Okay. Now we come to the next point, which is activity. So what exactly is activity? Okay, we said that radioactivity we can measure, and we define activity to measure that. So what exactly is going on? Let me explain that to you. So suppose there is a container. Okay, there is a container, and in this container we filled a lot of X nuclei, where X is radioactive. Okay, and only X was present, and this was the initial moment. Okay, so this is T equal to 0. Okay, now because X is radioactive, at a later instant, it is quite possible. In fact, that will be the case. Okay, that will be the case that apart from X, we will also find some other. Nuclei. This is the one in which X is getting converted. Okay, so this would be the situation. At a general time. Okay, so some X have already converted into Y. Okay, which means that if initially the count of X nuclei was N0, okay, now the count of X nuclei is N, where it is less than N0. And what happened to the difference? Like N0 minus N. This was the initial number, this is the current number. So N0 minus N, that is the number of Y nuclei that we see here. Okay, that is the number of Y nuclei that we see here. Okay. Now, after a small amount of time, let's say after dt time more, after a little bit of time more, can we expect some more X nuclei to have converted into Y nuclei? Like, okay. So what we can expect is that at T plus dt, the number of X nuclei is a little bit less than N. Because some nuclei got disintegrated within this dt duration. At this point, those dn nuclei, they were still alive. They were still in the form of X. Let's say disintegrating into Y means death of a nucleus, let's say. Okay, so here those dn nuclei were still alive, and here they have now disintegrated. So dn nuclei have disintegrated in the time dt. Okay, again, to give you an example, like it's not a very good example, but let me give it to you. So let's say a pandemic struck, we all are aware of pandemic. So this is a city. Initially, before the pandemic, it had a population. Okay, let's say it has a population of 1,000. Okay, now pandemic struck, we knew that every day some people are dying in the city. Okay, we observed on 12th day and we saw that out of 1,000, only 650 people are left. Okay, so that was the situation at 12th day. We came back on 13th day and we noticed that now from 650, only 630 people are left. Okay, so these 20 people died on between the 12th and the 13th day. We can say they died on the 13th day. So what is the rate of death in this city right now? So that would be 20 divided by 1. So 20 deaths per day is what is happening at the 13th day. So that is the instantaneous rate at which the population is decreasing. Okay, so that is what activity is. Activity is the number of nuclei, the rate at which disintegration happens. Okay, this is rate at which disintegration takes place. That is called activity, and it would be defined as dn mod by dt. So this is minus dn by dt. Okay, because dn itself would be a negative number, n is decreasing. Okay, so that is how we define activity. The unit of activity is dps. Dps is disintegration per second, and it is also called as becquerel. Okay, so 1 becquerel is 1 dps. Okay, all right. Okay, so this is the activity. Now the theory of radioactivity suggests that activity of any sample is proportional to the number of nuclei left in it. Okay, activity of any sample is proportional to the number of nuclei left in it, which means that activity can be written as some constant into n. So initially there were more nuclei, so initial activity was more. Then with passage of time, the number of nuclei of X are decreasing, so the activity is also decreasing. So gradually the activity keeps on decreasing. Okay, here lambda is called the decay constant. It is called decay constant, and it is a characteristic property of the nucleus. So for example, for carbon 14 it would be something different. For uranium 235 it would be different. Uranium 239 it would be different. So it is a characteristic property of the nucleus. Okay, and when we use this equation in this format, like activity can be written like this, and then when we do the math, okay, when we do math, which I'm not doing right now, okay, we end up getting this, that n is equals to n naught e raised to power minus lambda t. So this equation is called decay law. Okay, this equation is called decay law. It tells us that how many nuclei are left after time t. Okay, it tells us how many nuclei are left after time t. If I make a graph of this, it would be like this, n versus t. So the initial count was n naught, and then it decreases like this. Okay, so it becomes 0 after infinite time. Okay, it becomes 0 after infinite time. So this is what is called as the decay law. Now there's one thing to understand, that n by n naught, okay, is same as the mass left divided by initial mass, the number of moles left divided by initial number of moles, the activity divided by initial activity. All of this is same. Okay, all these ratios are same. So whatever equation we wrote, you can write that in terms of mass, in terms of moles, in terms of activity. Okay, so all of this is interconvertible. All right, guys, so this is all related to there's one more small thing that I want to communicate. Let me just do it quickly. So there is something called as half-life. Okay, what is half-life? So half-life is the duration in which the count of active nuclei becomes half. For example, if the half-life of a sample is 2 hours, then initially, like at start, I took, let's say 10,000 nuclei. After 2 hours, it will become 5,000. After 2 more hours, it will become 2,500. After 2 more hours, it will become 1,250. So after every 2 hours, it will just keep on getting half. That is called half-life. Okay, and if you do the math, like how can you do the math? Let me just show you. So if you put n naught by 2 here, because we are saying that after half-life, this becomes half of the initial value. So if you put n naught by 2 here, and then you do the math and you try to find the value of t, you will get that t half. Okay, the t half is ln2 by lambda. ln2 is 0.693, okay, and which is almost 0.7 by lambda. So this is half-life, okay, and if we try to write the equation in terms of half-life, e raised to power minus lambda t, lambda can be written as ln2 by t half, so this transforms to 2 raised to power minus t by t half. So even this is used in many equations, or if the half-life is given to you in questions, you can make use of this version of the equation. Like, what do I mean by this version? You can write n is equals to n naught 2 raised to power minus t by t half instead of going with the lambda version. If you are given lambda, use this. If you are given half-life, use this. That will make calculations a bit easier for you guys. All right. So that finishes our radioactivity chapter also. I hope you were able to understand a lot of things from this. Okay. It's a good chapter. It's a very scoring chapter. If a question comes from this, then there are good chances that you will be able to solve those questions. So study it well, guys. Okay. I'll see you next week. Take care, everyone. Bye-bye.